Hello, my name is Neiheiser, and I'm going to be presenting you our work Anthemius Efficient and Modular Block Assembly for Concurrent Execution. I'm currently a postdoctoral researcher at ISTA, and this is joint work with Lefteris from Eastern Labs. The presentation is going to be structured as following. I'll first start with a short introduction before I head into the fine details of how Anthemius works, and then I'm going to finish up with the evaluation and conclusion. So everybody wants to build better, faster, and higher performance blockchains. And that's why high performance blockchains are currently all the rage, because they're trying to meet the ever growing transaction demand. However, blockchains have a lot of different components and a lot of different bottlenecks at different locations. And while consensus has significantly improved and has not been that much of a bottleneck in the recent years, there's still a lot of other bottlenecks in other locations. And in this presentation and in our work, we will be focusing on the execution engine, where there's still a major bottleneck. And to be precise, the bottleneck here is the execution of smart contracts. For once, smart contract execution is still often done sequentially, like on Ethereum, which has led to the emergence of parallel execution engines. And there's vastly two main types of execution engines. For one's optimistic parallel execution, like Block SDM, and then guided execution, like in Solana or Sui. Optimistic execution executes all transactions optimistically in parallel, like the name says, tracks conflicts as they rise, and then re-execute transactions if conflicts are detected. Meanwhile, in guided execution, user hints or some kind of hints are used to build an execution schedule where conflicts cannot arise. They have different trade-offs. For one's optimistic parallel execution might have a high overhead and very contended workloads, as it requires a lot of re-executions. Meanwhile, guided execution might be more difficult to integrate in existing blockchains because you require now some sort of hint mechanism, which might result in a higher application development overhead if they're required by the users, and it might also be overly pessimistic. That means sometimes we don't know yet which resources we're going to access, so we have to reserve all of them. However, the performance of parallel execution does depend heavily on the workload, and that is because we cannot parallelize what is sequential. So if a lot of transactions access the same resource in a read and write manner, we cannot easily execute that in parallel. And if we look in how the resources are distributed nowadays, we did a little bit of a study here, we can see that resources are heavily contended. For example, on the average day, Uniswap, around 30% of all trades are on the same coin pair that have to then be executed sequentially, which significantly limits the parallelization potential. And on the very contended days, it's even over 45%, which doesn't allow parallelization beyond 2 cores pretty much. And this is what Anthemius tries to solve, because at the moment, a single popular resource like a coin pair, NFT, or game affects the latency and throughput of all the transactions in the system. So Anthemius is a modular and novel block construction algorithm located at the block proposer, so a leader-based system, and maximizes the throughput of parallel execution and avoids these popular resources from delaying independent transactions. Let's get into the details. Anthemius is, if we remember back before the architecture, situated between consensus and the mempool. It queries the transactions from the mempool, and then consensus fetches blocks from Anthemius instead of from the mempool directly. Let's give you first a high-level idea. Let's imagine execution scenario with 4 cores from the bottom to the top, and then execution time of the block from left to right. And ideally, it looks like this. So we have all 4 cores fully utilized for the entire execution schedule of the block. The problem is that in reality, it looks a little bit more like this, where we have one or multiple applications with very long paths, and then the remaining cores are idle for the rest of the execution time. And quite often it even looks like this, so that even 2 cores are almost completely idle for the majority of the execution time. So what we try to do with Anthemius is then to cut these 2 long sequential chains apart delay the next part to the next block, and then pad the free space with other transactions. And ideally, it looks then something like this, where even the actual overhead then for this long sequential path is also minimal, because this all had to be executed sequentially anyway. And the only overhead we have is then the scheduling time between the two blocks. The problem is, though, that this is an NP-complete scheduling problem, and scheduling may take longer than execution speed up we obtain, which makes it not worth it. So ideally, we want a really greedy approach somewhere in the ON realm that does this very fast and still has a decent speed up. The way we do this is with two main components. We have the batch handler and the batch scheduler. The batch handler queries the transactions from the mempool, divides it into evenly sized batches, and invokes the batch scheduler, while also tracking the success rate. The batch scheduler is then where the actual logic happens, which I get to next. So the batch handler works more or less like this. It receives the transactions from the mempool, divides it all into even batches, hands the first batch to the batch scheduler where the actual scheduling happens with some set of parameters, receives the block back with some kind of inclusion rate, and will then can adjust the parameters depending on the situation when handing the next batch to the batch scheduler. The batch scheduler then, like I said, tries to produce a block out of one or multiple batches, and is the one that handles all the dependencies and costs of the transactions. This also means that it does require some kind of dependency hints. They're either user given or then have to be provided by pre-executing the block. The way this works is the following. So we get this batch from the previous batch handler that we have here, and then we start going through the different transactions. We go through the transaction, we check in the dependency tracker. X doesn't exist yet in dependency tracker, so we add it to the block, update the value in the dependency tracker, and then go to the next transaction. It's again X, it is in the dependency tracker, but 1 plus 3 is still below our limit of 10, so we can add it to the block and update the dependency tracker, and then we can go through all the different transactions, update the dependency tracker accordingly until we reach the fifth transaction. Now, the fifth transaction has a gas cost of 8, which plus the 4 we already have would exceed the maximum limit, so we cannot add it to the set of transactions, and we have to delay that to the next block. So the batch scheduler this way has an O1 dependency tracker access through like a hash map, and given n transactions and an average degree of E dependencies, we have then an ON times E complexity, which is very cheap. We have some additional rules I didn't explain here because it's a little bit complex for this talk, but you can also check in the paper for more details. But we are also avoiding some transactions that unite a lot of hot resources in the middle of the block, because they can then increase the dependency tracker of all the other transactions and limit the parallelism. And we also have some things with sequence numbers, because if a user submits transactions with sequence numbers, we cannot reorder them, obviously. So let's see how the results actually look like. And we implemented this on top of Aptos and Chiron. And the batch handler has around 70 lines of code, and the batch scheduler 120 lines of code, so it's very modular. We evaluated this on an AMD EPYC 64-core processor, so we could really see how this improves over a different set of number of cores. We used the Chiron benchmark, so we used real-world workloads with DEX, NFT, peer-to-peer, and a mixed application workload. And we have it both for guided execution, like in Solana or Soy, using Chiron, and optimistic execution, like you have it in Aptos, by using block STM. And we have always providing two kinds of bounds, and coupled setting, so the lower bound on the performance, as if the scheduling cost would go on the full critical path of consensus, and a decoupled assumption, which is then the higher bound on the throughput improvement. And we varied it, like I said, from 4 to 32 cores, and at a target block size of 10,000 transactions. This means that for the vanilla versions of Chiron block STM, they would always get 10,000 transactions, while Chiron might already finish scheduling before that because it cannot find any more transactions to speed up for the given block. So the performance for Chiron is already over a multi-block setup. The way the results are, we have from the top to the bottom, the different workloads and the throughput and transactions per second, and on the x-axis the number of worker threads. In the first workload, the NFT workload, we can see that the performance is very similar, even though we don't have a disadvantage here. The performance is still very similar, and that's because of the details I mentioned earlier with the sequence numbers. The NFT workloads has a very low number of users, so that each user appears many times in each block, and that's why we cannot speed up the transactions meaningfully here. However, in the main part, we can not only see a consistent speed up over all cores, but we could also see that it scales when we add more cores. By using Anthemius, the performance improves and doesn't stagnate. And in the last workload, the mixed workload from Solana, we can see that the performance goes up until around 12 cores and then also stabilizes, because it's a very complex workload to schedule and there's a lot of transaction interdependencies here. Now, if we compare this to the performance compared to block STM, in the case of optimistic execution engines, the performance looks already quite different. Once we see that block STM has sometimes these little spikes in the beginning, that's the case because for the optimistic execution engine, there's sort of a optimal set of number of cores where it has the least number of conflicts and doesn't have to do a lot of re-executions. And then again, we cannot reschedule the NFT workload meaningfully, but we can do it for the peer-to-peer workload, for example, very well, where we can see a performance improvement above 24 cores. And for the other three workloads, and especially the mixed workload, we still see a very nice performance advantage that stagnates because we cannot fully take advantage, because even though we can give block STM a block that can technically be executed in parallel, block STM doesn't have the context information to take fully advantage of this. Now, the interesting thing is now, how does this affect the latency of the transactions? Here we have a box plot from the 1, 3, and 5 batches. The box plot means the box ends at the 75 and 25 margins. The points out and to the bottom and top are the 90 and 10th percentiles, and the yellow line is the median transaction time. Now, it's very important to note here that what we mean with the batches is that we have the first batch of 10,000 transactions, and we're gonna try to finish the full first batch. And that's the latency for all the transactions of the first batch. We already included a lot of later batch transactions at this point, but we didn't include them here because we really wanted to see how the original batch transactions are delayed. And for 3 batches, we finished the first 3 batches, and we have already included a lot of later transactions, and for 5, it's the same thing. So if we look at the results here for the mixed workload, we see that initially we have a very similar median with a little bit more of a range. We have a decent speed up on the 12th percentile, but otherwise it's very similar, and a slight delay on the 75 percentile. But the more batches we have, the more delayed and contested the vanilla execution engines get, and the larger the advantage in terms of latency also gets, so that our median becomes better than the 25 percentile, and our 90 percentile is around even the median of the vanilla. That means we have a very small latency overhead here only. So, concluding, Anthemius offers a up to 240% speed up, speeding up the majority of transactions with a lower latency, is very modular without security trade-offs. It's very low cost actually, so that we have a scheduling cost of around 10 milliseconds to schedule 10,000 transactions. And it also creates a very healthy incentive for blockchains, because if someone accesses a lot of hot resources and delay the entire blockchain, they should also either be delayed or have to pay a lot more for this, so that the entire blockchain is not slowed down significantly. Thank you for listening, and in this version, your questions will have to go in the comment sections. Thank you for listening.